So in this question, the problem was in fact regarding the evaluation of the so-called Fourier transform. In fact, continuous time Fourier transform of h of t to find h of omega. But implicitly, we saw this, we have seen this during the system response concept. Okay? When you want to find the Fourier series coefficients at the output of a system, we had to multiply the input Fourier series coefficients by h of omega at the corresponding omega, at the corresponding frequency. And over there was a formula which relates h of omega in terms of h of t, right? There must be a formula like that. You may remember that. That formula will be our new chapter, which is the continuous time Fourier transform. That is the very definition of continuous time Fourier transform. That was the formula. We will continue with that. But before that, it's not in the curriculum and it's not in the book, but there is a relation between the discrete time Fourier series and the famous discrete Fourier transform, which exists in the MATLAB functions. In fact, if you want to do Fourier analysis in computers, what you have is so-called discrete Fourier transform, DFT. And in MATLAB, the function which invokes this thing is FFT. It is just a fast implementation of discrete Fourier transform, and the abbreviation corresponds to fast Fourier transform. All right? So in computers, this is what you have. But meanwhile, what you have is automatically discrete time Fourier series as well. What I mean is this. If you have a discrete time periodic signal, let's say like this, with period 4, then it repeats itself, right? Like this, to the right and to the left. So the period is equal to 4. And how many discrete time Fourier series coefficients do we have? Distinct Fourier series coefficients. We have 4 AKs. A0, A1, A2, and A3. And A4 will be equal to A0. A5 will be equal to A1, etc. It was also periodically repeating itself. Now, these Fourier series coefficients are exactly equal to the FFT of this vector, which corresponds to these 4 symbols. So it is periodic normally, but as you see, it also corresponds to a finite segment of a vector of length 4. And that vector, when you invoke, for example, FFT in MATLAB and say FFTX, it gives you a list of 4 numbers. An FFT or a DFT is an n-to-n transformation. It's a discrete transform, in other words. When the input vector size is n, the corresponding FFT size at the output is also n. And those n things are nothing but the Fourier series coefficients of the periodically replicated version of the signal. So that's what it is. Okay? I'm telling you as a side information, and it usually doesn't exist even in digital signal processing course books either. But you usually use FFT in MATLAB for Fourier analysis, so you should be aware of what you're finding when you use FFT. When you use FFT, what you find is nothing but the discrete time Fourier series coefficients. But it is also related with the Fourier transform. And the Fourier transform, we will see, it's not this chapter that we will see, but it's one after that, the next chapter, regarding the discrete time Fourier transform. And the discrete time Fourier transform is a transform which takes some finite signals and converts it to the frequency domain. And that frequency domain thing that you will have will be in continuous axis of omega. This one, the FFT which are Fourier series coefficients, are in fact samples of those Fourier transforms. Usually what you want in engineering is the Fourier transform. Your boss will require the Fourier transform. He or she wants to see the plot of the Fourier transform in continuous frequency axis, omega axis. But you don't have it. You have some vector numbers in MATLAB because everything is digital in computers. Those numbers are nothing but samples of that discrete time Fourier transform. Okay? So how do you get a more accurate representation? By increasing the number of samples. And the way to do it is to take this thing, this vector, and extend from the left and from the right by padding zeros. You put many more zeros. Those larger vector will be your new x vector. Let's call it x prime vector. Now how many samples are there? Let's call, this is 4 and this is, let's say, 64 samples. When you take FFT of this thing, you will have 64 samples at the Fourier domain. Not 4 AKs, but 64 AKs. And it will be a more accurate or more continuous representation of the Fourier transform that we will be looking for. So it will be a better picture that you will obtain. You just have it by padding more and more zeros. But this is a DSP issue, but even this DSP issue is not handled properly in DSP, digital signal processing books. So for the curious students, this is what it is. Okay? When you take a look at MATLAB, you have FFT, and this is what FFT really corresponds to. Now we can continue with our chapter, or we can start with our chapter, which is the continuous time Fourier transform, or to be more precise, it is the Fourier transform, we can say. And I will skip the details about how to achieve that, but I will write it down because you already have it in your notes. Remember that h of omega was equal to this integral from minus infinity to infinity, h of t e to the minus j omega t dt. And in this integral, this is a time function. This is also a time function parameterized by frequency. And when you integrate through time, no t variable will be out. This will be in terms of omega only, which is the frequency of this harmonic. This was valid for a system. H of t was the impulse response, and this was called the frequency response. Now what I will immediately tell you is that that relation, or the same formula, is valid for signals as well. And what you get is not the frequency response. It's not a response anymore. It will be just the Fourier transform. And the notation will be a little bit different. According to the book by Oppenheim, it doesn't represent the Fourier transform as h of omega or x of omega. It represents it as x of j omega. So, but that j is the complex square root of minus one thing. It's not a variable. This is a function of omega, and it is no different than this. It's the same thing. It's just a notation, and the notation will be more critical when we proceed towards the so-called Laplace transform. Because in Laplace transform, and you should know it already, that Laplace transform thing, because it was covered in differential equations. In differential equations, do you remember that S thing? That's how we were solving the question. That S thing is j omega plus, which is purely imaginary, plus a real part. So it is an extension. The Laplace transform, Laplace parameter of S is an extension of this thing. And in order to indicate that this is purely imaginary in the argument, it's the j omega part of S, in other words. S is sigma, which is real, plus j omega normally. So this is the only j omega part that comes into the picture. That's why it is indicated as x of j omega. It's just a notation. Is equal to the same integral, x of t e to the minus j omega t dt. And this formula is the Fourier transform formula, which represents your time signal over a completely new axis called the frequency axis. Because normally we plot our functions as a function of time. It changes in time. The axis is the t axis, x of t. But as you see, or we will see, this is a one-to-one transformation which exists. Therefore, the same function of x could also be represented over a completely new axis of frequency, omega. Of course, it needs an inversion for the existence, and the inverse Fourier transform, let me just write it immediately, is a similar integral of h of j omega e to the j omega t d omega. So they resemble each other, right? In this thing, the complex exponential is with a negative exponent. Here it's a positive j e to the j omega. And as you see, the right hand side, this is a function of frequency. This is also parameterized in terms of frequency omega. And when we integrate through omega, omega is gone, and we are left with the only parameter, which is time. So the output of this integral is a function of time. It's a pity that sometimes in exam questions or things like that, we encounter, or I encounter, answers like, what is the Fourier transform, I ask? Well, that's a function of omega only, and there must be no t inside it. But the students give me a function in which there is t somewhere. It can't happen. There is no t parameter in the Fourier transform output. And there is no frequency parameter in x of t. That must be a function of time. Okay? You should be careful about these things. This inverse, I'm telling you to be like this, but the way to obtain it is nothing but by construction, or you can verify this formula. Indeed, I can ask you an exam question like this. Prove that this formula is the inverse Fourier transform. And how are you going to do that? What you have to do is, just, by the way, it's not h, of course, I'm sorry about that, it's x. Just put this definition of x of j omega into this x of j omega. Put it here. And it will be a double integral. I would use a different t for this integral. Let's call it t1, t1, and t1 here, and put it like that. And then evaluate that double integral, and you will come up with x of t. That will be the verification. Other than that, I don't really want to go into the details of how to construct this inverse formula. That's not very difficult, but it will take some time, so let's skip it. For our purposes, we should at least know these two formulas. And you have to exercise a lot. You have to evaluate a lot of Fourier transforms, and you have to evaluate a lot of inverse Fourier transforms as well. Let's start exercising then. How can we find the, let's say, Fourier transforms of some of the signals, including that quiz question? For instance, x of t is equal to e to the minus a t u of t. This is our first example. And what is that? It's an exponential. Let's assume a is greater than 0. It's an exponential, and depending on the value of a, of course, it may be a decaying or an increasing exponential, but since it is positive, it's a decaying exponential. Times u of t. So it goes as 0 until 0. And when t is equal to 0, e to the 0 is 1. So it jumps to the value of 1 and it decays like this. This kind of a signal is what we have. And how can we find the Fourier transform? These are the first examples. Therefore, the formulas that we have will not be very difficult to evaluate. From minus infinity to infinity, x of t. What is x of t? It is here, e to the minus at u of t. This is x of t. And e to the minus j omega t dt is the integral that we need to evaluate. Now notice this u of t, which forces time to be greater than 0, because for time less than 0, this is 0, and every multiplication term will vanish. So I can equivalently write it from 0, not from minus infinity, but from 0 to infinity for time. Because for time less than 0, there is nothing because of this u of t. And we have e to the minus at, e to the minus j omega t dt. Again, from 0 to infinity. Let's put it in the same exponent form like this. E to the minus parentheses a plus j omega t. Let's write it like this, dt. And what is that? It's an exponential, and exponentials are the easiest things for integration. It is 1 over, with a minus sign, so minus 1 over a plus j omega e to the minus a plus j omega t. This thing, this is the integral, and we need to evaluate it from 0 to infinity like this. All right. Now there seems to be some problems here. First of all, this is a complex exponential. In other words, the exponent angle term contains some imaginary parts. So what can you say about e to the minus a j omega t at t is equal to infinity? It is 0 indeed, because of this a. And this a is positive. So the real part, in other words, is positive. So minus at will definitely vanish. It will shrink down to 0. Despite this j omega t, which will never vanish. But it is in the multiplication form. It's just an oscillation. That oscillation with this one will cause a decaying oscillation. Decaying down to 0 at t is equal to infinity. So t is equal to infinity, this will be 0. Minus, what is the same thing at t is equal to 0? When t is equal to 0, this is e to the 0, so that's 1. Then we only have 1 over a plus j omega with a minus sign. So minus 1 over a plus j omega, but there's also another minus here. It's minus 1 over a plus j omega, which makes a plus 1 over a plus j omega. Or in short, it is 1 over a plus j omega. So that's it. This is the first Fourier transform that we discovered for this x of t. Now, since it's a complex valued function, the way to plot such functions is a little bit problematic, and there is a single way of drawing those things. We need to plot h of j omega, x of j omega for this case. We need to plot x of j omega. But how are we going to do that? Because it's complex. We will plot first the absolute value, which is the magnitude, and then the angle, which is represented like this, of x j omega. We need to plot two things, in other words. In a majority of purposes or applications, this magnitude is more critical than the angle, because this magnitude describes whether it's a low-pass filter, a high-pass filter, a band-pass filter, if it is a filter. If it's a signal, it says whether it's a low-pass signal, a high-pass signal, a band-pass signal, etc. So most of such information is carried in the magnitude, not in the angle. But of course, there are other applications or purposes where we need the angle term as well. So what is the magnitude of x of j omega? In order to find this term, the magnitude term, the most practical way is to multiply x of j omega, the complex thing, with its conjugate. When you multiply it with its conjugate, any term and its conjugate, when they are multiplied, what you find is magnitude squared. That corresponds to that, right? That is complex calculus. So just multiply that thing with the complex conjugate, and then, since it corresponds to magnitude squared, take the square root. So we need to write it like this. Times this, and then we need to take the square root. And that will give you square root of 1 over a squared plus omega square. So this is the magnitude in terms of omega, and since it's now real, of course, you need to, or you can at least plot this. There's a way to plot it. By the way, it's always positive. It's a magnitude. There is nothing negative or something like that here. It's always positive. Where does it reach to its maximum? And how does it decrease? For what values of omega do we have larger numbers or smaller numbers? When omega is small in magnitude, if it is 0, for example, then this thing will reach to a maximum, because omega is in the denominator, so we want to minimize it. If it is negative number, since we are taking the square of it, it still increases the denominator, therefore the overall term, which is the magnitude, will decrease for negative omegas, and it will also decrease for positive omegas as well. When omega is equal to 0, it reaches to a maximum of what? 1 over a. And a is already positive, so we don't need to put a minus sign or anything. It is 1 over a. That 1 over a in time decreases. You may even try to plot it in tools like MATLAB, like this. Okay, it decreases. For example, when omega is equal to a, so this is 0, and this is the axis of omega. When omega is equal to a, it is 1 over a squared plus a squared, or 1 over 2a squared, which is 1 over square root of 2 times this thing. So this is 1 over square root of 2 times a. Do you remember from circuit theory that what this may correspond to? When the magnitude reaches 1 over square root of 2 times the initial magnitude, what was this frequency point? Cutoff frequency for minus 3 dB, right? Minus 3 decibels. So this A will correspond to, omega is equal to A will correspond to a cutoff frequency if it's a filter. Same here. It's minus A. I'm putting legends just for illustration purposes. It's not very much critical for us. But it's like that. As omega increases, this thing decreases even more, lower than 3 decibels, in other words. So what can we say about the behavior of this signal? What kind of a signal is this?
Low.
It is low pass, because a majority of the energy is condensed in lower frequencies, and it decreases as frequency increases. It's a very bad low pass signal. It's far from being ideal. What's an ideal low pass signal? It should be a rectangular box like this. That would be a perfect low pass signal, but this is, well, a first order approximation, we have to say. And you will know why we call it a first order approximation, because such signals like this in time appears from first order differential equations. It's an answer to a first order differential equation. So first order systems will generate these signals. Of course, we haven't seen the angle term yet. The angle term you may or may not remember properly, but it is like this. That is the angle of x of j omega is equal to the angles in the numerator angles in the positive sense, and the denominator angles in the negative sense. We need to just sum up several angles here. In many cases, remember that x of j omega was 1 over a plus j omega. In many cases, x of j omega is a polynomial of j omega in the numerator, and it's a polynomial of j omega in the denominator. And every first order polynomial like this will induce an angle. For example, the angle here is, it's the arctangent of what? The imaginary part over the real part. So this is the angle of this denominator. If it is a multiplication with another angle, then you have to add another arctangent of that term, omega over b this time, for example. But they are in the denominator. Therefore, this angle of x of j omega is equal to minus theta, which is minus arctangent omega over a. And if you're curious again, you may even try to plot this thing. It is something like this, I guess. At a, the angle is minus pi over 4, because when omega is equal to a, omega over a will be a over a, which is 1, and the inverse tangent of 1 is 45 degrees, pi over 4. And minus of it is minus 45 degrees, or minus pi over 4. Because tangent of 45 degrees is 1. Okay? And similarly, at minus a, it is 45 degrees, pi over 4. And it's an arctangent form, like this. So this is the plot of the angle, if you wish. Right? Okay. Let's continue with another example. A strange example. X of t is equal to delta t. What is the Fourier transform? Now, can you see the difference between the continuous time Fourier series and the continuous time Fourier transform? As you see, the examples now are not periodic anymore. Because if they are periodic, then we need to find the continuous time Fourier series for periodic signals. That's what we have. But this example that I erased was not periodic. This example is not periodic either. It's just any signal. For any signal, we have Fourier transform instead of Fourier series. So x of t is equal to delta t, and therefore what is x of j omega? It's the integral xt e to the minus j omega t dt, and we need to put the input here, which is delta t. And how do we evaluate such integrals. Well, if there is a multiplication of an impulse inside an integral, that's a piece of cake, because this impulse exists in only one place, which is t is equal to 0. At all other instances, this is 0. So this multiplication thing should be evaluated at the instance of existing delta t only, which is when t is equal to 0. What is e to the minus j omega t when t is equal to 0? It is 1. Therefore, it's the area under the impulse that comes out only, which is 1. Now, what does that mean? It means the Fourier transform is 1. Is it a function of omega? Sort of, yeah. It is constant. For all frequencies, when you plot it over the frequency axis, it is a constant value of 1. Now, what can we say about low pass, high pass, band pass, and things like that? Behavior of this thing. It is an all pass system or a signal, which is one of the hardest signals that can be encountered. In physical reality, it doesn't exist. It shouldn't exist. But when you take a look at the Fourier transform, which is x of j omega, and when you see a shape like this, it has a very famous name. When you look at the Fourier transform, it is constant everywhere. There's a name to that. No, that's not it. It is usually a noisy behavior, a noise-like, because noises have low frequencies, high frequencies, very high frequencies, everything. This is something like that. And there's a name for this noise, and there's even a film with this name. White noise. But of course, white noise is a random signal. We haven't seen random signals, and we are not going to see random signals. But this signal, xt is equal to delta t, shows a white noise characteristic in the spectrum. And do you know why this name is given white? No, that's the color's name. It's the color of sunlight. Okay, white color. A white color contains all the colors, all the bandpass colors in the visible light spectrum, ranging from blue to red. Okay, so every color is inside white. That is something like this. Blue is somewhere here, and then we have other colors. Purple, I don't know, green, yellow, orange, and then red. So everything is equally existing. If all the colors equally exist, then that's a white color. That's why if all the frequency band is flat like this, they call it a white noise. That's where the name comes from. And interestingly, you may notice that a prism, a triangular prism, into where a white light comes in, and as we all know, all the visible spectrum goes out scattered like this from optics. So this thing is nothing but an array of bandpass filters. It is just splitting all the frequency content of this white into here, like the equalizers. So physically, that's the meaning of frequency, or that's the analogy that we can find from physical reality. But anyway, that is x of t equals delta of t. Now, let's come to the quiz question then. What was this, 1? T minus 1? Was that the question? Because it doesn't matter what kind of a delay you put. X of j omega is from minus infinity to infinity delta t minus 1 e to the minus j omega t dt. Now, where does this delta t minus 1 exist? at t is equal to 1 only. Only. All the others will be multiplied by 0. So this thing exists only at t is equal to 1. What is the value of this part when t is equal to 1? E to the minus j omega, isn't it? So we have delta t minus 1 times e to the minus j omega only. T is equal to 1 times dt. Now see that this thing is not a function of time anymore. It becomes a constant, which can be taken out of the integration times the integral. And what is the right hand side? What's the integral? It is 1. It's the area under the impulse. It's a shifted impulse, but the area doesn't change. So the answer is e to the minus j omega only, which is the answer, which was the answer to the quiz question. Let's continue with a more involved example. By the way, can you plot the magnitude and the angle of these things? I guess so, yeah. It's just from the Euler's formula. It is cosine omega minus j sine omega. Therefore, from the imaginary and the real parts, you can always find the magnitude and the angle. Now let's go back to this. At least I can give you one very simple answer to the magnitude of this. If you want to plot, in other words, this magnitude of x of j omega over omega, what is it? 1. Because e to the j something always has a magnitude of 1. Okay? I guess you can find the angle, of course. Now a more complicated example, not as simple as the others, but this is also a very famous one. It's a rectangular box again. From minus t1 to t1 it is 1s, and everywhere else it is 0s on the time axis. And the notation, the analytical formulation, is given as 1 when the magnitude of t is less than capital T1 and 0 else. So in a question, in an exam question, it could be asked like this or it could be drawn like this. And if it is not drawn already, it's always a very good idea to first draw the plot of this x of t and then evaluate. From the formula. And in this formula, x of t is sometimes 1 and sometimes 0. It is 0 for all time instances from minus infinity to minus t1, and from t1 to plus infinity. It's always 0. Only in between minus t1 and t1, it is 1. So the integral exists only from minus t1 to t1, and over there x of t is 1. So we only have this. 1 times e to the minus j omega t dt. And we need to integrate or take the integral. And it's a complex exponential, as simple as the first example that we have seen. Just you have to substitute the integration limits. And when you substitute them, you will find this, after simplifications, of course. This. All right. 2 times sine omega t1 over omega. This has a very famous name. There's a name given to this. For T1 equals 1, particularly, for T1 equals 0.5 or 1 over 2. For T1 is equal to 1 over 2, there is a famous name to this one. Then it becomes, x of j omega becomes sine omega over 2, because omega times T1 will be omega over 2, and it will be divided by omega over 2. Okay? Because there is a 2 in the multiplication form, so in the denominator it is a further division of omega over 2. It is also known as a sync signal. That is the name. It depends on your definition. Okay? It depends on how you define the arguments. But that's the shape of a sync signal. And a sync signal is a signal which handles the situation at omega is equal to 0. Can you see the problem when omega is equal to 0 here? Because in the denominator there is an omega. That's a problem. So when you divide by omega, it means you divide by 0 when omega is equal to 0. But a further problem is that the numerator is also 0 when omega is equal to 0. Because sine 0 is also 0. So how do you find the value at omega is equal to 0? Hospital's rule. Again, you need to apply the Hospital's rule. You have to take the derivative of both sides. The top side will become a cosine and the bottom part will become a constant value. And that constant value indicates that the power, the strength, zero strength of sine and the zero strength of theta itself are the same. Sine theta is approximately equal to theta when theta is small. In other words, that is the Taylor's expansion formula of sine. When theta is small, sine theta is equal to theta plus a constant times theta squared plus another constant times theta cube, etc. It goes on like this. When theta is small, theta squared is even smaller. Theta cube is even smaller, so the dominant term is theta. Which means that when omega is 0, this thing will be exactly the same as the bottom part. And it says that sinc of 0 is therefore equal to 1. So there is no singularity when omega is equal to 0. And the overall shape is an oscillation that decays. Why does it decay? Because as omega goes to infinity, the denominator will go to infinity. The numerator, it's just a sinusoid. It is oscillating. The denominator is increasing. Therefore, the overall envelope of this thing is decreasing as frequency is increasing at both sides, like this. So this is the name of and the structure of the famous sync function that we will see. And a rectangular signal has a Fourier transform of a shape called sync. That is something that many students just continue remembering even after graduation. If it's a rectangle signal, its Fourier transform is a sync function. Okay, that's something that I'm sure you will remember. Most of the students do. Even though they may not remember anything else, this thing is very commonly used because most of the other examples that we will see will be distorted versions of the same example. So we will start from the sync formula in the Fourier domain, and we will distort here as well. As this signal distorts, the Fourier transform will also distort. So we need to know this association as a starting point. So let's give a 15 minutes break. We will continue.